this is not the theorem, this is just a correlation. Correlation is called virial theorem. So we will just talk about the case when xi is qi and xj, we put it as a pj. So, and we have a system of the n particle. So n is the number of the particles, and we have a 3 degree of the freedom for each particle. So Q1, Q2, Q3, or P1, P2. So degree of the freedom of the system is 3 for one particle. And you have a 3 particle, so you have a 3n state in the phase space. So I want to talk about only this case. Let's see what happens if you substitute that here. If you substitute that here, you get this expression. So according to the Hamilton equations, so from the dynamics Hamilton equations, you know that the partial derivative of this will be q dot j. So, and if I is equal to j, so you get q dot j kt delta ij. So this is just a special case. But the case which I want to study is exactly the other option. The other option is that I want to consider the case when both of the xi and xj are considered as a q. So qj. You will see that the quantity which will appear here as the expectation value will be like a visual work in classical mechanics. It will be like the work which you done on the particle to move it from the one point to the other point. Let's see to clarify my statement. So qi1 partial qi q. What's that? So according to Hamilton equation again, this will be minus pi dot. So it seems that a quantity appear here for the one particle, and this quantity is very important quantity. Qi dot j. This quantity is called virial for one particle. Virial function. Very soon I will show that the virial is proportional to the pressure. Very soon I will show you that this is proportional to the pressure. And pressure multiplied to the volume. And as you expected that, it will give you the equation of a state between the pressure and the T. But I want to find it that. Okay, so if you have a set of the particles, so this is the virial for one particle. So virial for the one particle is that qi p dot I. What is the p dot I? This is the force on the one particle actually. If you consider the cube here, this is the cube. If this is the direction q1, q2, q3, so for each direction, fi, and here I is 1, over the qi, it gives you, this is a p dot I, f is p dot I, dp dt. According to the Newton mechanics, you know from the basic mechanics that the force is the change in the momentum. So instead of the p dot I substitute fi. Okay. What is the F? So from the basic classical mechanics, you know that you can convert the F to the pressure. Pressure is defined as the normal force over the area yes. So this force I can write like P dot the area. What's the call it? dA. P. As a result, the area for the one particle will be minus for one particle minus QI P dA. So for each particle you can write this equation. Actually this equation is should be written in the differential form, but you will understand that this is just for one particle. If you want the total area, so will be sigma via I from 1 to n. Yes? And not from 1 to n, actually 1 to 3n, because each q are changing from 1 to 3, and you have n particles, so I can write 3n. So, and you have a small parameter, a small quantities here, which they are defined and the infinitesimal differential forms for each area dr. So you guess that this sigma tends to the form to the integral. So 1 is integral of p, and for I need to specify the area also. For each qi you have one area element. For example, in the direction of q1 you have a dA1. In the direction of the q3 you can define dA3, and therefore direction of the q2 you can define dA2. So they have the same indexes as you can see here. And if you write it in 3 dimensions, it will be all the dr. Yeah? Can I write that? Q1 dr1, Q2 or dr2, and Q3 dr3. So I can write it in the form of that. Okay. So we consider the system in equilibrium, and we consider the pressure as a macroscopic parameter for the system. All of them, what does it mean? That it means that I wanted to take the pressure as a constant here. I mean, it's not a function of the coordinate, the pressure. It's a function of the temperature. If pressure be function of the coordinate, it means that the system has some anisotropy or inhomogeneity. What does it mean? It means that the density of the gas here, for example, is different from here or here. So it's very difficult situation. So we make this question as much as we can simple. So we consider the gas as a system with homogeneous, so density is the same everywhere. Density of the matter, I mean the gas exactly. Not the density of the particle in phase space or something. That already passed the Liouville theorem. We are talking about the simple gas in the box and just study the properties of this quantity. We call it the Brillouin. So by the very much simplification, we can set out the P. So this will be your integral over the surface. Which surface? For each of the surface, you can have this integral. So Gauss-Stravinsky theorem show that the integral of anything multiplied to the area over the area surface can be written in divergence as d volume. Sometimes we should not be confused. We write the volume cubic and the area too. So instead of the F, you have the vector R. So integral of the R dr will be divergence of R d cubic x. What is the divergence of R? 3. You can calculate it by different ways. So it will be 3 integral of the cubic, so it will be 3v. Yes. get minus 3 PV is the right hand side. The other side will be, and you remember that you make it one summation here, yeah, over the virial. So this summation must done also here for that, because one time you get the summation in the left hand side, for right hand side you didn't include. So car T, sigma car T from I to 3n. So it's just simply give you 3n car T. So So as you see, we can find from here the equation of this state. The only things which there is only one thing about the direction. It seems that we have one extra minus here, huh? It seems that minus 3 PV is equal to 3n cut. This is wrong. Because the equation of a state should not have any minus here. What is the missing part? The missing part is that the area always is outgoing vector, but the pressure as a vector is to the inside. So one thing which we needed to be very careful is that when we make it the dot here. So in this case, we can write that the pressure, if you consider the pressure as a vector, and dA are in the opposite direction of minus b here. So I can write it 1 minus here just to guarantee this minus d. That was the thing that I was thinking why we have 1 minus. So minus to minus will be plus. So you get 3 PV, 3m car T. So PV m car T is the equation of a state for the gas. So but you didn't get anything new, yeah? You calculated that before from the counting the state like omega. But I will use this approach for the gas with interaction. And that's very new for you. When you have the gas molecules in the interaction together. So the interaction can be any form of interaction, like the electromagnetic interaction or the gravitational interaction. But gravity we don't consider, because consider the gravity for the molecule in the box is very incredible. So we are not talking about that. You can think about the next step of this calculation will be, that was no interaction here, nothing. We just think about the system of the gas in equilibrium. So next step is I will use this virial concept to calculate the equation of a state for the gas, and the gas is in the interaction. So there is a relation between the expectation value of the virial and the expectation value of the kinetic energy. So actually, by very simple calculation, you can show that the virial is -2 of the average of the kinetic energy. Kinetic energy is sigma p squared over 2m, I from 1 to 3n. What you will do is that we need just to find the expectation value of the kinetic energy according to the equipartition theorem. So average this will be average sigma pi squared over 2. And this you will do like that. You will write sigma pi I1 to 3n. Look at what I will do. Instead of the pi, yeah, I can write in terms of the partial derivative of the Hamiltonian. And you can use the equipartition theorem. So Anyway, as I told you, it seems that the virial is not something new, it's just integral of the pressure. But I will use it that in the our case. So I want now start to study the system of the not ideal, yes, ideal. Still is, we have ideal gas, but interactive ideal gas when you have the interaction. So studying the interactive model of the ideal gas, fix it in the box. So a toy model for operation of state of an ideal interactive gas. So first of all, you need to know that which kind of the interactions the molecule can have. If there is a gas inside the box again, so there is a large number of the particle here sitting. So one particle is labeled by the I, so the second particle you can label by the J. So you have a lot of particle here. And depending on the physical parameters of this particle, you can have different type of the interactions. The main idea is that the interaction between the particle, so if you call it this potential, you can call it U or V anyway. Uij is the potential energy between interacting particle. The idea is that the potential energy between interacting particle should be function of the distance between them. Only the function of the distance. So it will be U as a function of the Rij. U as a function of Rj minus Ri. But not all the interactions are like that. For example, if you consider the particle with a spin, then the interaction between the two particles with the spin is completely different from that. If you have a two particle with the spin S1 and S2, so this will be the interaction term. There is no any R here. Huh? Such system we don't consider now, the system with the spin or. We just consider the system when the interaction is a function of the distance between the particles, R and Ij. The I means that to find the equation of a state for them. So I wanted to find, so the goal is to find this equation, PV over N per T equal to what? For non-interacting gas, it will be 1, of course, yeah, PV is N per T. So non-interactive, you will have some extra terms or corrections when you have in the presence of interaction. So I want to find these corrections. Basically, it's a very hard question because you need to find the potential first. Which kind of the potential you have it here, and also you think you are looking for the whole system. So you need to know about the quantum mechanics for this system. So this is a many-body particle problems, and a few examples of the many-body you can solve exactly. So it needs the approximation methods, like cluster expansion or something like that. Forget about all the quantum mechanics like perturbation theory or many-body particles. So we are going to use the concept of the virial here. Let's see what you can get from the virial. Okay. We just consider among all of these particles, we consider two particles, I and J, and we consider the interaction between them. So it will, and Fij is the force from I to J, and Fji is the force from J to I. And this is the distance between them. And if you have a coordinate system, you can write this Ri and you can write this Rj. So the vector between them, we call it Rij, is Rj minus Ri.